Ryan DeLugo. I'm an undergraduate senior.
I'm Joshua. I'm also an undergraduate senior for mechanical engineering.
And we are from UT San Antonio. We're here from Dr. Daniel Pineda's Laser Spectroscopy and Chemical Propulsion Laboratory. And our project will be over the design, analysis, and manufacture of a vacuum pump sound-dampening enclosure in a compact form factor. This is just the presentation outline. We're going to walk you through the process as if you're building the enclosure with us. So first we'll discuss the project objective, then we'll discuss our enclosure design. We'll also go over our computational fluid dynamics and computational heat transfer analysis, as well as our parametric analysis. Then we'll go into the manufacture of the vacuum pump enclosure, discuss our results, give our conclusions, and our acknowledgements.
For our main objective is to build an enclosure for 2 vacuum pumps within the lab. The main problems with the vacuum pumps is that they create a lot of unnecessary noise, acoustic noise, and vibrations. So we're going to reduce those as well as improve lab safety from the said acoustic noise.
The motivation for this project is that the lab actually had a previous vacuum pump enclosure, but for one single pump, but unfortunately it did overheat due to a cooling system failure. So the lab had expanded, so we got 2 more vacuum pumps, and now we're designing an enclosure for the 2 vacuum pumps instead of 1. And this enclosure will be beneath the shock tube's inertial mass, which presents a design and manufacturing challenge.
My primary concern, additional to the noise, is that the vacuum pumps generate a significant amount of heat, starting from 104 degrees Fahrenheit to 118 degrees Fahrenheit under normal laboratory use. So we want to reduce this heat with proper ventilation without heat buildup inside the enclosure, so that the vacuum pumps can perform efficiently without compromising the experimental accuracy.
And so our cooling solution is that the enclosure uses 2 chambers connected by a labyrinth path to control both airflow and sound transmission. This path will reduce the noise while directing air through the enclosure for circulation and exhaust, and 4 fans were used to maintain cooling.
The material selection, we chose materials that is easily found by the acoustic performance, the cost, availability, and feasibility. The enclosure design integrates a rigid structure, a reflective barrier, and absorptive material for sound control and insulation. Together, all these materials achieve sound control while also maintaining a compatibility with the laboratory space.
So first, we have the material selection for the enclosure structure. We selected dense particle wood panels, and this was to provide rigidity and increase the enclosure mass. So the added mass reduces the wall vibration and also improves sound isolation. Wood filler and flexible sealant were used for the gaps, and this was to prevent sound leakage.
For the reflective barrier, we chose 1 pound per foot squared mass loaded vinyl for the soundproofing layer. This added mass increases the resistance to vibration and sound transmission. This also reflects the sound back into the enclosure, whereas it can be further absorbed by the insulation.
And for the absorptive layer, we selected 1.5 inches thick of mineral wool. And the reason we selected this is because it is made of closely packed fibers with small air gaps that force sound to travel through the material.
And for the labyrinth path, we chose a maze-like channel structure so that the sound vibration and sound waves can travel the longest distance before exiting. So this can allow for the reflective barrier to repeatedly bounce with the sound waves to reduce any noise and vibration, so it can also be dissipated along the way as well.
And this figure is just our enclosure layout. So this is the top view. In the center chamber right here, we have the 2 vacuum pumps. And then the red arrows are going to be the sound source. So when the vacuum pumps release the sound, it's going to go through and then out through the sides, out both cooling fans. And in the back is just the vent exhaust, and that the blue arrow is going to be the direction from which the air flows. And then this black outline is going to be the wood panels as well as the labyrinth section. And then the pink is going to be the mass loaded vinyl, which is the reflective layer. and the blue is gonna be the mineral wool, which is the absorptive layer.
For the CFD and CHT analysis, the CFD was used to model airflow, the pressure and fan performance of the enclosure, and the CHT was used to evaluate the heat removal and predict the internal air temperatures near the pumps. This simulation process was used so we can find any problems within the enclosure and validate any type of airflow, heat sources, and so we can monitor both the temperature and pressure drop. The parametric analysis was also performed to optimize the chamber width and exhaust vent size to provide the best cooling performance and the pressure drop as well.
So our simulation goals and outputs was that surface goals were used to monitor the inlet and outlet temperatures, as well as the pressure and the flow rates. So the pressure drop was evaluated to ensure sufficient airflow throughout the enclosure, and the values decreased from about 30 to 40 pascals to 10 to 20 pascals as the vent width increased. So this analysis predicted that the cooling performance based on internal air temperature near the pumps.
For our fan selection, we chose 4 140mm Noctua NF A14 fans for ventilation. These fans can provide a sufficient airflow along with the CFD and fan curves that were used. And these simulations were conducted using 2,000 to 3,000 RPM based off of if you need more cooling. And the goal is to maintain the pump temperatures below 104 degrees Fahrenheit for steady operation.
And for our parametric analysis, the enclosure was simulated beneath the shock tube's inertial mass, and this was to verify packaging and clearance. The CAD geometry was iteratively updated to improve ventilation at both pump locations while also meeting the space constraints.
And for the setup, the parametric study was performed to evaluate how key design variables can affect the enclosure's cooling performance. This was also modeling the enclosure geometry using the chamber width and the exhaust vent size, while also monitoring the temperature flow rate and pressure drop. And measures also used to balance the accuracy and computation time, while also lowering the resolution for initial trains and higher resolution for accuracy, as well as a medium resolution for efficient parametric analysis.
So for the chamber width, which is where the vacuum pumps are going to be, it was varied from 24 to 36 inches to evaluate cooling performance. Changes in the width showed minimal impact on the pump inlet temperature, and 30 inches was selected to fit 2 pumps comfortably. This was for clearance for tubing, access for maintenance while meeting the space constraints. And the 2 figures here on the left, you can see the chamber width of 24 inches, and on the right is the chamber width of 36 inches.
For the exhaust vent width, the exhaust vent's length was fixed at 18 inches, while the width was varied to evaluate its effects on the cooling performance. By increasing the vent width, it reduced the pump temperature rise from 19.7 degrees Fahrenheit to 13.9 degrees Fahrenheit, and also lowered the absolute pump inlet temperature from 91 degrees Fahrenheit to 85 degrees Fahrenheit, that indicated improved heat removal and more efficient cooling.
And our parametric analysis results is that it showed that the chamber width had minimal impact on temperature, while the exhaust vent size significantly improved the cooling performance. And again, these are the same figures I've shown previously. The left has a 24-inch chamber width, and the right has a 36-inch chamber width, just so you can see the difference in between, like how much space there is between like the walls and the vacuum pumps.
For the funnel geometry, the outer geometry was based off of a trapezoidal design so it could fit under the shock tube within the lab. And the layout was to maintain sufficient clearance for both the pumps and their operating connections, while also meeting spatial constraints, so no issues with the lab or equipment can be found.
And this is just our engineering drawing after we conducted our CFD, CHT, and parametric analysis. This is what we are going to be building in the next slides.
For the overview, the enclosure is built in stages using common shop tools within the machine shop in the engineering building of the UTSA. We first assemble the wood frame and the internal divider layout to lock in the final labyrinth geometry, and then install the mass of the vinyl and mineral to seal and use the caulk to seal all joints and mounted the fans, and then finally added the exhaust vent and attached the plexiglass door for the final enclosure.
So prior to building, we did meet with our graduate student mentor. In the figure to the right, you can see me meeting with Joseph Hernandez McCloskey just to make sure that we were on the right track to building the enclosure.
In this next picture, it was just us dimensioning and cutting out all the wood panels so we can make sure everything is correct in length and width, so nothing can happen with the enclosure.
After we had cut out all the wood panels, we then painted the wood with Rust-Oleum black paint and left it outside to dry for 24 hours.
The next step, we installed the bottom and front and back sides of the enclosure so we can then also measure and make sure everything fit correctly.
Next, we drilled in all of the holes for the screws. This was just to make things easier on us later.
This picture here shows the enclosure on the inside as well as the final shape of the enclosure with everything installed, including the sides and the top panel.
Next, we stapled in the mass loaded vinyl. Again, this serves as the reflective layer in the enclosure.
The next step we used was we placed an 1.5 inch mineral wool on top of the mass loaded vinyl to provide insulation for the heat pumps.
Next, we cut out the plexiglass door and screw door hinges. So the reason we chose a plexiglass door is so that we could visually see the vacuum pump's oil levels. Because what happened with the first vacuum pump is that we weren't able to see the oil levels because it was just completely black, and so the vacuum pump had overheated.
This next step was just us screwing in the fans into a custom 3D printed enclosure or fan mount that we then screwed onto the enclosure.
Next, we added the exhaust vents. After we had completed all this, our enclosure was pretty much done.
And this is the picture of the final enclosure with the plexiglass doors installed, the wheels, as well as the top cover to hold the pump vents in place.
After we had finished the enclosure, we did have to transport the enclosure all the way across campus. Fortunately, the enclosure did fit, but unfortunately we did not measure the dimensions prior. Luckily, everything was able to fit through the doors, but we did run into some issues.
And here's a picture of the enclosure within the laboratory space with everything installed. The picture on the left side is with the two vacuum pumps, and the picture on the right side shows the tubes that will be covered by the flap on top.
And these are our results. So we measured the noise levels prior to building the enclosure, and it was approximately greater than 75 decibels. And after we built the enclosure, it was between 55 to 65 decibels. So the decibel scale is logarithmic, so we reduced the sound level by at least 10 times of absolute scale, which is pretty significant.
And for our conclusions, the enclosure reduced the sound levels by a significant magnitude, and that students within the laboratory are all very pleased, as well as the faculty. However, we will need to install a plate underneath each pump, just in case any oil leakage or any issues for the pump may happen.
And these are our acknowledgements. We would like to say thank you to the following individuals. So first, Christopher Huseman, Dave Wessler, Orlando Favela, Bombshot Abedi, Jacob Peoples, Donovan Yelder, and Aubrey Fuse for their assistance throughout this project.
And this has been our presentation, and these are the pictures of us bringing in the wood and our contributors as well. Do you have any questions for us?